join, and when most of you have joined, I will class. Okay, let's. I'm here. I want to as many of you as possible for begin the class with.
Okay, sir.
Okay. Well, let me just okay. Turn on my camera and introduce myself. Okay. My name is. So I'll be taking you through programming class for Switch block 2020 the fundamentals of program, learn developing such a program. Then what we want to do is that we want to delve into solving. Okay, pick a problem and then break it down and then look at how we can use program knowledge or skills and tools with regard to devising a solution, common or everyday. Okay, so I will take this class with all of you. I think the majority from the or the work center, you are supposed to be on the WhatsApp. Sorry, on the other, but on in any other center, you're supposed to be in this link. Okay, the please so that you can follow along. I will have some slides, okay, just to make the learning interactive as possible. But I'm going through everything directly from the manual, okay? So you follow me from the manual. You can able to follow along. When there are questions you can raise, you can able to raise those questions and I will answer or respond to all those questions in the right time, okay? So the manual or the module is our course outline. I think there are sections of it which are not currently in the module you are holding, but we will let you have all those sections so that you can use them and then you can understand the course and then you can deliver when it's time to write the exams. Okay, but anything you need, kindly feel free to maybe type it in the message or in the chat section. I would need the course rep or maybe the yes, type it yes. Okay, those who are yet to join. Okay. So I would need the course rep to the course reps. I know that there are various centers, so the course reps to get in touch with me so that I can so that we can get to know and the various centers, and if we need to compile a list for any other thing, we can compile a list for any other thing. Okay, so please, if you have any experience in programming, that's fine, but if you don't have any experience in programming too, that's also very fine. Okay, so we'll teach you the rudiments of programming as it comes. Okay, yeah, so that's it. I think at this point we have 26. Let's see if we can push up to about 40 and then yeah, but then next week we will not wait for people. Okay, once the class starts, we'll start. I know this is the first week, so it's a bit hazy for most of you, so once the class starts we'll start. Okay, so I'll just hang on for a few minutes and then wait for a bit and then I will start our lecture very soon.
Mr. Emmanuel J, please turn off your camera.
Okay, hello. So can we begin? I think we have about 33, okay? So let's begin very quickly. If you open to the first chapter, unit one of your module, we are going to talk about the history of programming, where programming began and what programming is. It's all about. So kindly open to unit 1 and then let's begin. So we'll do first session. Now, in this session, we're going to look at the introduction to computers and programming languages. We're going to look at the history of where computing began from, modern day computing, where it began from, and then we're also looking at the history of programming languages, some key milestones in programming languages, and then types of programming languages, and we'll pick the types and then we'll explain what the various types of programming languages are, and then we'll look at language translators at the end. Okay, so when we say a computer, what is a computer? Okay, so unfortunately the module doesn't begin like that, but we need to understand what a computer is. So you know that most of us from our secondary school, we understand that a computer is what? A mechanical or an electronic device that is used to process data or information, convert that data or information into meaningful facts or meaningful information. Okay, so in order to process that data into meaningful information, we need to be able to manipulate that data. We need to be able to store that data. We need to be able to do lots of stuff with that data. Okay. Now we know that, or we get to see that computers cannot work on their own. Okay. Now there are two main components. What we mean is that when we say computers cannot work on their own, we see that there are two main components of a computer system. There's what we call the software, which is a set of instructions that tells the computer how to perform a particular task. and then the hardware, which is the physical part of the computer that you see. Now, when you just buy the hardware and you take it home without a software, you cannot use the computer. And then when you just get the software, you need hardware to install the software on. Okay, so those two things are very vital for computers to run meaningful operations. Okay, now where did computing begin from? Okay, so we learned that before time, or before we began to record history of computing, we humans always had an urge to do counting. Okay, so our desire to make counting easy is what led to our development of tools to help us compute. Computing came from the idea of compute. Okay, and the first of these tools are stones that our forefathers used, sticks our forefathers used. We had what we call tally system. So you do down, 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 do you across, that kind of system. And then we had other kinds of mechanical, which are non-electronic systems. Okay. Now, early history records a device called an abacus. An abacus is used in ancient Asia and I think Middle Eastern, or maybe Arabic places where abacus was used to do complicated counting. Okay, so these days our children in the nursery school and in the primary school, they use the abacus to do mathematics. Okay, and then that device is a computer. The stones, the sticks, and all those other mechanical devices are computers. Now, when we began to build mechanical watches, someone or people like Blaise Pascal. Pascal was a famous inventor, and Pascal built something called the Pascaline. In fact, quite recently, one of his Pascaline machines was sold for over $500 million. These devices were like watches. They had wedges and all sorts of moving parts in them, and their main function is to help the user do addition and subtraction. Okay, right? Their main function is to help the user do addition and subtraction. Okay. Now, Blaise Pascal was not the only person, right? Someone like Gottfried Wilhelm, okay, he also built something called the stepped renocker. And then Charles Babbage built something called the analytical engine. All of these are inspirations for our modern day computer, but they didn't look like anything that we built today, because the things we use today, which we classify or call as computers, are or have electricity flowing through them or have electronic parts, but those computers do not or did not have electronic or moving parts. Then we have someone like Herman Hewlett, okay, the owner or the founder of Hewlett Packard, right? He built something called a tabulating machine, and this machine was used to do the census in the US. Okay, then fast forward, when electricity began to be used, someone like Vannevar Bush, he built something called the differential analyzer. Konrad Zuse in Germany built a machine called the Z1, the Z3, the Z2, and the Z3 during the World War II era. Then Hewlett Akins built something called the Mach 1. It was a very big calculator or very big computer used for calculations. And then the famous example of a modern day computer, which works almost like what we use today, is called the ENIAC. ENIAC stands for Electronic Numerical Integrator and Computer. And these were amongst the first generation computers. In fact, they don't look like anything. You can Google any of these names, and the device or the pictures you see are computers which do not look anything like what we use today. The difference, or the reason why they don't look like what we have today, is because today we have miniaturized what a computer looks like, or we have reduced the size of a computer, and we have built technology which allows us to reduce the size of what a computer is. Okay. Then we had people like Eckhart Presper and John Mauchly. They built what we call the UNIVAC 1. and we have other developers and other technologies come up, like, for example, transistors came up, and transistors reduced the size of computers. Integrated circuits also contributed to what we have, smaller devices today, ICs, very large scale integration, very large scale integration, and all sorts of technologies. But around the 1980s, we've had the first IBM PCs, and the Apple computers began to come off the processing line. And so computers have come a long way. But what we want you to understand is that their history predates electricity. Okay, so anytime that anyone was doing anything that involves calculation or used a mechanical device to do calculation, they were doing computing. Okay. Now let's look at the history or some milestones in programming, since our course is about programming. Now, Charles Babbage, when he was building his analytical engine, he had an assistant called Ada Lovelace. Okay, so Ada Lovelace was one of the first people to write what an actual computer software should look like. Okay, so she wrote a routine for Charles Babbage's machine, and that formed the foundations of what an algorithm is today. Okay, Conrad Zuse also wrote something like that, something similar. And then we, around the 1949 thereabout, when we began to build electronic computers or electronic devices, we had a symbolic language they used called the assembly language. Okay, and then this developed further into a programming language of a high level of sorts called Fortran. Fortran is the first high level programming language. It was built by John Backus for the IBM computers. Okay, then Lisp was built to do AI, and then COBOL was also developed around the 1959 thereabout. Okay, now Algo and BASIC were built to simplify, so they came around somewhere around the 1960s and 1970s. C also came about, and then we had object-oriented C++. So C++ was the first object-oriented programming language. We had Smalltalk, we had Java, and Python came off the processing line. And since then, we've had lots of different languages like Swift, PHP, Kotlin, so many modern languages. And now with the revolution of AI and data science, we've had languages like R, which have come to revolutionize the way we do AI and machine learning. Okay, so computers have come a very long way, and they've come, and the programming languages have developed in conjunction with computers, because wherever you need a computer, you need software to run or manage a computer. Is that understood, please? If you have a question, kindly put up the question in the chat. I will try. The class is being recorded. Okay, the class is being recorded. Okay, let me get. It's being recorded. Okay. Okay. The class is being recorded. Okay, so don't worry. They will provide you a link to the recording so you can get access to the recording. Okay. 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 So let me continue. Okay. So with the evolution of programming languages, have also come with the evolution of what we call paradigms, the styles, the ways in which we pick the programming language and write in them. Okay, so we've had several evolutions or several changes in the way programming is done. Okay, we went from sequential to procedural to object-oriented to functional to visual to, in fact, declarative. We've had so many different styles of programming languages evolve over the period. Are we okay? Okay, so programming languages have also evolved over the period, and this has caused or has energized or changed the way software is also developed. Okay, now one would ask, what is programming? So programming basically is problem solving that uses a programming language. So when we have a problem and we're solving it and we're using a programming language, we call that programming. Now, programming involves the use of programming language instructions or commands. Those instructions are also called syntax. So usually you will hear that I will mention syntax. When I mention syntax, we are talking in the domain of problem or program language commands. Now, there are four main classes of programming languages. We have machine languages, we have assembly languages, we have high-level languages, and then we have scripting languages. Now, machine language and assembly language are regarded as low-level programming languages because, of course, you hear us say high-level. When we say high-level, then somebody will ask, okay, so what are the low-level? So the low-level are the machine languages and the assembly languages. Are we okay? Now, what is machine language? Machine language is basically the low-level programming language that a machine can understand. It usually consists of a high or a low bit, what we call a binary digit, or we sometimes write it as 0 and a 1. 0 being the absence of electricity or a charge, and 1 being the presence of electricity or a charge. If there's any question, kindly let me know so that I can address it from the manual that you are reading. I'm following the manual, so you can go back to the manual and check all of this information out. We are currently looking at let me see which part of the manual. We are currently looking at session 1, unit 1. Okay, we are on, I'm trying to explain low-level programming languages, and I'm looking at list of some low-level languages, and I'm explaining what assembly language is, what machine language is. Okay, I hope you can follow me from there.
Sure, sir.
Okay, so I get a thumbs up and follow me from there. That's good, okay. So machine language basically is the low-level bits or on and off bits which represent the presence of a charge or the absence of a charge. Now, machine language is difficult to actually use in programming a machine because human beings are not used to understanding zeros and ones, long sequences of zeros and ones, okay? And so it becomes a bit difficult to memorize and use that pattern, right? For example, if we are only using machine languages, it will be difficult to teach you the programming because you have to now learn bit patterns, okay? Now, because we wanted to make things easy, we built something simple on top of the machine language. We call that assembly languages. Now, what assembly languages are a way to, it's a form of symbolic programming where we don't have to write zeros and ones, but instead we can write maybe add or move or sub or divide or something, right? We can write a simple English phrase which will cause the machine to do what the zeros and ones represent. Okay, that's why we call it symbolic programming. Now, if you look in your manual, you see examples of this symbolic programming. You see the add, the subtract, and all those several different examples that we're talking about. Okay, so the assembly language sits on top of the machine language. It is, even though it is also written in English, which is easier than the zeros and ones, but it is still very technical. Okay, so we need another level to help us write human readable and understandable programming languages. So we programming programs. Okay, so we built something called the high-level programming language. Now, the high-level programming languages are designed to be easier for human beings like you and I to read, to memorize, to learn, and to use in our coding. Okay, so they contain English phrases and they are very simple. In fact, when you pick any of these high-level programming languages, you can see that most times they are very simple and they are readable. You can understand what they mean. They are usually guided by something called logic. Okay, so examples of high-level programming languages include what? The Fortran, the Pascal, the Lisp, the C++, the JavaScript, the Java, Objective-C, the C, Visual Basic, and all of those simple programming languages that you've heard of, HTML, CSS, all of those are examples of the high-level programming. And now, why do we call them high-level? Because they have certain features. One of those features is called abstraction. Abstraction means that you want to hide or make something complex as simple or appear as simple as possible. So instead of writing sequence of zeros and ones, zeros and ones, 0, 1, 0, 1, 0, 1, 0, 1, instead of that, you just write add 1 plus 1. Okay, so adding 1 plus 1 to you, you are adding 1 plus 1, but to the machine has to understand the zeros and ones. What the high-level programming language does is to hide that 0 and 1 away from you, so that when you write add 1 plus 1, the machine on its side will do the zeros and ones and then get an answer and return the answer to you. Okay, and is that high-level programming languages are readable. They are very simple. They are readable. The syntax or the rules we use to learn or to read high-level programming languages are very simple to read and understand. Okay, they are portable. Portability means that you can move them from one machine to another. In fact, you can install a program written in Java on your Android phone. You can install that also on your iPhone. You can also install the same program written on your desktop. You can also install that on your MacBook or any other operating system. Okay, and then another key feature is what? Productivity. They help you learn the programming language faster and work faster. You don't have to learn zeros and ones or any technical stuff. Once you pick an easy programming language, you just learn the syntax, how the programming language picks the rules, and it becomes easier. And then some other features include what? Advanced features like what? Modularity, data structures, user interface, and all those things. It becomes easier to use. It is easier to use high-level programming language just for your programming than to use zeros and ones, which are machine language or symbolic programming like assembly language for your program. Are we okay? I hope we are okay. Okay. So in high-level programming languages, we should have, or you often hear of terms like source code. Source code represents the code that you, the programmer, will write. Okay. Code that you, the programmer, writes. And then sometimes it's called machine code. Okay. Now it must be translated into low-level programming language. In fact, the computer does not understand any of the C++ or the Java or the C or any of those other programming. In fact, there must be a translator on your machine which translates the Java into zeros and ones for the computer. And those ones are called language translators. Okay. So there are two main kinds of language translators. Okay. We have the we have the interpreters, and then we have the compilers. What an interpreter is that an interpreter is a type of language translator which takes the statements and tries to execute the statement just as you have written them. Okay, so interpreters take the statements and they try to execute the statement just as you have written them. Okay, then a compiler is different because what it does is that it takes the whole program you have written and tries to translate the whole program into zeros and ones. We call that a target or object code or executable. Okay, so an interpreter is different from a compiler because an interpreter translates the statements line by line, just like your pastor and the translator in your church. So when the pastor says one line, the translator will translate that one line. So that example is called an interpreter. Okay, then for the compiler, the pastor will read his whole sermon, and then the translator will now translate the entire sermon into zeros and ones for you. Okay, so I have summarized in this table a few key differences between compilers and interpreters. Okay, and examples of what is classified as a compiler and what is classified as an interpreter. Okay, so these are the key things. I think some in your module, but you can use them as general knowledge so that you can get a needed background to understand the programming we are about to do. Okay, Then the final class of programming languages are a section or a group of high-level programming languages we call scripting language. Now, what these are is that these are small kinds, or these are kinds of high-level programming languages which can be written inside the other. For example, if you want to write a web page, you need about 2 or 3 web languages like HTML, you need CSS, you need Python, or you need PHP. Now you can write HTML, you can write Python in HTML, you can write JavaScript in HTML, you can write CSS in HTML. Now, when you can do something like that, we call that type of programming language a scripting language. It's a very small programming language which does some small task, or it's mostly interpreted, and it is not too sophisticated in terms of its features. Okay, you can extend its features by adding plugins or add-ons. Okay, so examples include Python, JavaScript, PHP, ASP, Ruby, PowerShell, and all those other. Okay, any up to unit 1 session 1. Any question on unit 1 session 1? Yeah. Any questions? Any questions on unit 1 session 1? Can I ask at least one question if you will not ask me any question? Can I do that?
Yes, sir.
Hello?
Yes, sir. Okay, sir.
Okay. But you heard everything I said, right?
Yes, sir.
Yes.
Okay. So may I ask, what are some of the uses of computers? And someone type or mention some of the uses of computers. Okay. What are some of the uses of computers?
Sir, can I say that the computer is used to make work easier?
Okay, so practically, so when you say work easier, what do you mean by work easier? What is the use? What is the use? Okay.
Okay, let's assume we are doing calculation, that is computing, and the numbers involved are huge. So instead of taking a whole day to do the calculation, the computer can use a few seconds do the calculations for us.
Very well. Okay, so calculations. Okay, for data processing. Okay, that's good. That's good for education, for entertainment, for health.
For research.
Right? We can use data. We can use computers to manage health records.
For
right?
communication.
But note that all of these uses are as a result of software. Thank you very much for communication, Mr. George, for communication. Okay, so all of these are as a result of what? Software. So the hardware alone is not enough. You need software as well. For dating, wow, that's intelligent. That's very nice. Okay, so all of these are uses of
for research.
Computers. Okay. Okay, so now let's look at section 2 of unit 1. Okay, so what we are going to look at is hardware versus software. Okay, so we'll look at the basic components, and then we'll look in depth about what those basic components are, and then what computer software is, system software, application software, and then we'll look at the relationship between the hardware and the software, why or how they are working together, or they are working together. Okay, when we say computer hardware, we're simply referring to the physical components of the computer. Okay, the parts of the computer you can touch and see. Okay, because we cannot touch and see software. Software is intangible, but hardware is the tangible part. Examples are the keyboard, okay, the mouse, the keyboard, the mouse, the memory, the system units, okay, the camera, all of those things you can see and touch are the computer hardware. Okay, now when we look, or when we picture a computer system, we can picture it like these 5 things. Okay, so we have a central processing unit, something called the CPU. We have main memory or primary memory. We have secondary memory or secondary storage. We have input devices. We have output devices. Now let's look at them one by one. When we pick the first part, which is the CPU, CPU refers to what? The brain of the computer. That's where all the processing is done. Every task a computer is supposed to do is done at the CPU. Every task the computer is supposed to do is done at the CPU. Now, what the CPU is that the CPU consists of two key components, the ALU and the control unit. Now, the ALU stands for arithmetic logic units. That's where all the calculations are done. I told you initially that computers came up as a result of what? Calculations. Our need to build tools to help us calculate. And so, in fact, everything your computer does, everything your phone does, everything your laptop does, your desktop does, is actually a calculation. So it needs the ALU to do the calculation. Then the CU, or the control unit, is what controls the entire computer. Shutting down, switching on, letting inputs, showing outputs, turning something on, turning something off, the camera, the speakers. All of those things are controlled by the control units. Okay, and so these two components are inside this central processing unit. Usually, when you pick up a CPU, it looks something like this. You can see it down here. Okay, so a CPU looks something like that. It's a small chip you plug into the motherboard. Okay, every command the computer can do is carried out in the CPU. Usually, the speed of the CPU determines how fast your computer will run. These days, it's measured in gigahertz. Okay, gigahertz stands for what? Billion of a second. Okay, a billionth of a second. Okay, because it's so fast, we don't measure in seconds, we measure in hertz. Okay, so take note of that. Okay, then the next component which we will look at is the main memory. Main memory is also called RAM. RAM stands for what? Random access memory, or sometimes we call it primary memory. Primary memory is the staging area. For example, today I'm having a class at home. Okay, I have my computer on my desk. Okay, so main memory is like the desk. But when I'm done doing anything, okay, everything, I'll just pack my laptop and put it in my bag. The bag is permanent storage, but the desk is the storage which is temporal. When I'm done with my laptop, I can remove the laptop and then put on my desk a book. Okay, so notice that the laptop was removed and a book was put there, so it's temporal. We call that primary storage, right? And it's an example of what we call volatile memory. Volatile because when you switch off the power, everything in the main memory goes off. Okay, you lose everything in main memory. There's a hand up. There's a hand up. Someone just put your hand up.
Yes, sir. I wanted to
who is
know
that,
the
please? I thought I saw a hand up. Okay, Mel Mark Ishan.
yes, sir. When you were talking about the,
You can ask your question, please.
when you were talking about the CPU, you only mentioned that of the.
Hello.
Hello, sir. Hello, sir.
Hello.
Yes, sir.
Okay, so Mel Mark Ishan is not ready. Let's continue. Okay, you can type your question too in the chat if we are not hearing you. Okay. Did you hear her? Let me just ask. Did you hear her or him? I don't know what is that guy or lady.
Yes, sir.
Yes, sir. I heard her talking.
Him.
Hello, did you hear him?
We heard
Oh,
him,
you can
yeah.
hear him. Oh, okay. I cannot hear him. Oh. Wow. Okay.
His question was about you mentioned only
What
about
is he
the
saying? Someone
ALU.
kindly help him. We can hear him. Okay, so what's he saying?
He said that you mentioned only about the ALU and the CU part of the
Oh, someone help
CPU.
me with what
What
he's
about
saying.
the other part?
Okay, Mark, ask your question,
Can
please.
someone help me what he's saying?
When the question was about the CPU, I was he talked only about the ALU and then CU, but in some of the concept that we do, we know we also have the registers and then the cache. How do you call it, component? And I don't know. Now maybe I'm model. Whatever. I wonder whether maybe that one is not needed in this course, or something I wanted to him to talk about.
So did you hear him? I think he's mainly talking about
The CU and then the ALU.
that is it.
Okay.
It consists of the two, the ALU and the CU.
Yeah, and I said I wanted to know whether the registers and then that of the catch. I didn't know what I'm pronouncing the word.
No, those they don't come in when they talk about the components of the CPU. With the component, we have two. We just have only two.
So,
That is the main component, the main component of the CPU.
I think he went off, and I think he's off.
I think I'm sure, but it's still there. The picture is still there. I don't know.
He asked whether we can hear him at the comment section, and I told him no, sir. So maybe he's having a challenge with the network.
Oh, okay.
Also, Becca.
Hello, can you hear me? Yeah, can you hear me now?
Now we can hear. Yes, please.
For now, we can hear you.
Okay.
Cash.
Yes, sir. Yes, sir.
Okay, so I will try and then have us. So he was asking about the what do you call it? The other components in
about
the processor.
CPU.
Yes, there are other components in the processor. Okay, there's something called registers. There's a cache.
Yeah.
There are so many things in there, but because our class is centered on programming, we don't want to go beyond the limits of programming. Okay. Our class is centered on programming. We don't go beyond the limits of programming. We want to remain within that programming scope as much as possible, okay, so that most of you can understand whatever it is we are doing. Is that okay? So you do a class in computer hardware, and I guess in computer hardware, you learn about some of these things, okay? Okay, is that okay? Good. Okay, so let's go back to memory. Let's go back to main memory, and then we'll check out what is in there. Okay, so main memory, like I said, is also called RAM. Main memory consists of space that computation can happen on. Okay, main memory is like something like the work space. So when you come to work or when you turn on your machine, all the work that the machine is supposed to do is done by or is done in the main memory. Now, when you switch off the machine, then all of that work or all of the things you are doing in main memory are lost, okay, or it's lost, okay? So we call it volatile Okay. Okay. So now usually would have primary memory consisting of something called SRAM, right? We have SRAM and then DRAM, and then we have ROM. Okay, so SRAM, DRAM, and ROM, and then we have some other kinds of memory. So usually they look something like this. Okay, some of you have seen it before. When you open a computer, you see a module that looks like this. Okay, so this is the example of SRAM. Okay, these are examples of also these are DRAM examples as well. Okay, now away from that, we have secondary storage. Secondary storage is the space or the permanent space that we store or the permanent space where all your data which you don't want to lose are stored on the computer. Okay, so secondary storage stores the information permanently. Recall that when you have a photo on your phone, even when you switch off your phone, your photo is still on, right? Even when you switch off your phone, your photo is still alive. Should I say alive? But your photo is still on your machine. When the phone turns on, your photo automatically gets let's say your photo automatically is available on your machine when the photo or when the phone turns on. Okay, so the photo is kept in a place called secondary storage, and secondary storage is a permanent kind of storage, so it's non-volatile. When you switch off the machine, the information you store on your secondary storage is there permanently. Examples include hard disk, floppy disk, right? Something called solid state drive. I have photos of it. So you've seen this before, right? Most of you maybe have not, but a few older folks have seen something like this. It's called a floppy disk drive. It's a very small secondary storage and disk drive. Another example is the HDD or the hard disk drive. You've seen this before, right? In your machines, when you open it, you can see something looking like this. And when we remove the metal case, you can see disk and then a spindle that moves, and then a hand that moves to and fro from the spindle. Okay, then there's an example of a solid state drive. This one is also, this is a 1 terabyte, right? We have 1 terabyte, so 3 terabytes, and then they look like this. In your phones, we have something like this, or sometimes in your laptops, they have something like this as well in there. Okay. Then the last but not the least are the input and output devices. So input and output devices help your computer to collect or to enter information. So we can enter them through the keyboard, through the mouse, the joystick, the touchpad, the gamepad, the flatbed scanner. All of these are examples of input devices. Whereas so more input devices like a digital camera, your phone camera, MIDI or the MIDI keyboard or keypad, right? The stylus pen, the touch screen, all of these are examples. Then we have more like the webcam, the barcode reader, signature pad, smart card reader, and microphone. So your phone microphone is an example of an input device, or the microphone at church is an example of an input device. It converts whatever you say into a form of digital and pattern in which is sent out to the speaker. Okay. Then output device help us to display or to hear the results. So things like monitors, speakers, printers, headphones, plotters, braille readers, you name them, right? Today we have something called VR headsets. We have printers, we have speakers, we have monitors, we have projectors, we have the old CRT monitors as well, right? So all of these are examples of output devices. Okay. Now let's look at software. So what is computer software? Computer software or a program is a sequence or a series of instructions which perform specific tasks. So they tell the computer how to perform specific tasks. Whereas hardware is a tangible part you can touch, software is the intangible part you cannot touch. Okay, so for software, you cannot touch software, but for hardware, you can touch the hardware. Now, there are two main classes of computer software. Okay, we have the system software, and then we have the application software. System software is the software which controls and manages the operations of the computer. Examples include what? Utility programs, the device drivers, the operating system, and so many of them, right? We have that in, you can see examples in session 2 of unit 1, okay? Then we can have the application software, which make your computer very productive, okay? So if you want to do something like video editing, that one is a specific task. So you need an application software that does something specific for your computer, okay? Then we have examples like a web browser. If you want to browse the internet, you need a web browser. You cannot use a photo editor to browse the internet, but you can use a web browser. So those are specific tasks. If you want to write a Word document like a letter, or you want to write maybe a memo or something else, you need what? A word processor. We have spreadsheet applications like Excel. We have other different types of applications which make the user productive. So depending on what you are doing as a user, you can get a particular software that can make you productive. Okay, some of you I know are maybe accountants, some of you maybe are clerks, some of you maybe are different, you work in different professions, and all of these professions have particular software which make you productive in your profession. Okay. Any questions? Any questions? Any questions? Okay, no questions. Now we can also then we'll ask the question. So what is the relationship between computer hardware and computer software? Okay, so the key relationship is that computer hardware needs computer software. Okay, because if you just have the phone and there's no Android on the phone, you cannot use the phone. And then if you just have the Android, but you don't have the hardware, which is the phone, you cannot also use the phone. So the hardware and the software are important. But if you just have the hardware, even if you have the hardware and you don't have the latest software, you cannot do the job you want to do. For example, if I'm a teacher, okay, I teach and I need PowerPoint. Okay, currently I'm using PowerPoint to do the presentations. If I don't have PowerPoint, then I will not be productive. Okay, so software is very important, whilst the hardware is also equally important. Okay, so those who learn software, they are very important. Those who also learn hardware, they are also equally important. Now, the next section helps us to look at what are the impact of the hardware advances. Okay, how has improvements in the hardware affected the software? So, for example, the more we have advanced in the hardware, the more the software has also improved. Okay, I have a question. So let me hear your question. Let me hear your question. Once in the shower, standing up, please help clarify per slide on system software. Okay, system software. Okay, so I'll go back to system software slide and then I'll repeat again. So like I was saying, system software is the software which is used to control and manage your computer. So in order for your computer to turn on, to turn off, to do different things, okay, to maybe your sound is not working, maybe your sound is not working, maybe your network card is not functioning properly, or something is not working, okay, you need system software. So the example the gentleman gave, like the BIOS. BIOS is yes, a special type of system software. Okay, what it does is that BIOS boots the computer OS. Okay, BIOS is what boots the computer. It stands for Basic Input Output System. Okay, that is the software which boots the computer software. It's usually in something called the BIOS chip, and that is what loads first before every other thing can load. Okay. And then another person is asking, is the kernel also a system? Yes, please. The kernel is a system software. The kernel is the actual operating, the core operating system is called the kernel. Okay. That's the raw operating system. Okay. Without the UI and all those fancy things you see on the screen. Okay. 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 So if we get a hand up data, we can resolve that. So yes, so the BIOS and all those operating system and all those kinds of things are examples of system software. Okay. I believe we can go on. Okay, let's go on. So we're talking about how hardware advances have improved system software. Okay, now have improved software. So we also see that when memory capacity also increase, our machines are functioning very, very well. Okay, our machines are functioning well when our machines are functioning well when advances in computer hardware increased or improved. Okay, you notice that when maybe your at first your computer could only take maybe 2 gig, but now your computer the memory can take 4 gig, and because of that you can run games. You can run games which are very sophisticated on your machine. Okay, are we okay? So you can run games which are very sophisticated on your machine. So, and then we have some computers which are large computers. Okay, those computers can run very sophisticated hardware, right? For example, if you start to run those games on an old computer, the computer will freeze. But on these modern computers, they don't freeze. Okay, why? Because we have been able to advance or increase the storage capacity. Right, these days you can even store like 1 terabyte, 2 terabytes on a single drive. But in the past, we couldn't store such kind or such amount of data on a single drive. Okay, so those are also reasons, or these are also some of the advances that have come up. And then we have specialized software like GPUs. Okay, GPU stands for what? Graphics Processing Units. And then TPU stands for Tensor Processing Units. So these ones are special chips which help the computer to run very, very, very effectively or efficiently. Okay. Any question? Any question? Hello.
Hi. Hello, sir. Can you hear me? Please, can you hear me? Hello.
Okay, there's a question here. Says,
sir, can you hear me?
Wow. Okay.
Hello,
okay,
sir.
So it's not a question. Okay, so we can move on. Okay. Okay. So now we're going to look at the software development cycle.
Sir.
We're going to look at software development cycle and look at how software has evolved over the years. Okay.
Hello, sir. Hello.
Let's see. So kindly turn to session 3 of unit 1.
Hello,
session
sir.
3 of unit 1. Please, like I said, if you have any questions, you let me know so that I know how to help you with that. Okay. Okay. Okay, so we're going to look at problem solving, and then we're going to look at software development life cycle, something called the software development life cycle, or SDLC. Then we'll look at significance of SDLC in software development, and then best practices for writing and maintainable code. And then we'll look at testing and quality assurance. And then we'll look at software deployment and maintenance. Okay. Okay.
I can't hear anything. Oh.
I can't also hear anything.
Same here.
I think his
I think
network.
it's from his end. Yeah.
Yeah.
I think his network is giving him problem.
I think the network problem is general.
Someone should kind of let him, because when you are calling him, I think he doesn't hear anything. Either I don't know whether his volume or so that we.
Not the volume. It's mainly the network. It's mainly
Please
the network.
use the message option to ask questions. He said the network is not good, so use the message option.
All right.
Okay. Okay. I think I'm back. Hello. The audio went off. Sorry, I was online talking, but the audio was off. Forgive me. Okay. Can you hear me now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Sorry. The audio. I don't know. Sometimes the audio just goes off. I don't know why. But I'm online. I can see you. I can see you and everything. But I can't hear. You can't hear me, and I'm not able to also talk. I don't know why. Okay, so let's go back. So the software development life cycle is just a framework. When we say a framework, it's a structured means of, or a structured guide that helps us to develop software. Okay, now how do we develop the software? Okay, we develop software by first coming up with a plan for the software design, and then we will build the software system. All right, we'll build a software system. Then we'll test to see that the software system that we built does the job it's supposed to do. And then we will maintain it when we build it. Okay, so that's what the software development lifecycle helps us to do. Now, in your book, you see 6 steps. Okay, so I'll explain what each of those steps does. Now, what software development lifecycle, the first stage of the development lifecycle is sometimes you can add that to the requirements analysis, and then we can call those two things analysis. Okay, so what it does is that we have to understand the problem. Okay, before we can solve any problem, we have to see whether it is feasible to build the software or not. Okay, then we have to now gather the information, then what we need to build the software. Okay, that's what we call the analysis or requirements analysis phase. Then when we have gathered that information, we now have to do what we call design, architectural design. Just like how the architects build their building drawings by first drawing it, build their buildings by first drawing it. Software engineering, right? The second phase of the third stage, we draw the designs. We call that UI and UX design, right? UX stands for user experience design. Then we can now, after drawing the software, we now go and code the software. We call that implementation. And then after implementing or during implementation, we'll do what we call testing. Testing identifies problems. In software design, we call those problems defects. Okay. Then deployment is when we have finished building and then we give it to the client. We release the software to the client so that the client can use it. And then as the client is using it, occasionally we will send them, or we'll maintain the software. We'll send them updates. We'll change the way the thing is working. We'll move things here and there just to make sure that they have a lovable and an enjoyable experience. Okay, so this is a software development life cycle. It's a cycle because it all comes back to the same place. Okay, so it goes round and comes back, goes round and comes back. But we can do it in different ways. We call that development styles. Okay, so we have waterfall development model. We have the agile or the iterative development model. Okay, so you often find that in different places. Now, why is it important that we use a framework and not just get up and then write software? Why is it important? It's important because a framework gives us a structured way to design software, so that, you know, software or computer is a science, and so we have to have a structured way so that whatever you can develop here in Ghana, someone can sit in the UK and develop the same, or whatever the person in the US or China is developing, you can sit here, follow their instructions and develop the same. So the software development lifecycle gives us that structured framework so that we can see the results, measure well, estimate how likely or how unlikely a particular system will be developed, and identify all the problems or the potential issues that may result from the software design. Now, software needs to be properly tested, and testing is usually done during the development. There are different kinds of testing, like integration testing, system testing, acceptance testing, unit testing, right? And while software is being developed, just like water, okay? So I know that when you guys go to buy water, you normally would buy maybe a particular brand of water, like Verna, or maybe Belacqua, or maybe a particular brand, Pella, because you know that you trust that brand. That's the same with software. We need to develop software in such a way that people will trust the particular quality of the software we are designing. So when software is coming from maybe Microsoft, every one of you is certain that Microsoft will not give us software which will destroy maybe our computer, or which will ruin our maybe business. But once you buy Microsoft software, you know that you are sure that the quality is high. Okay, so same with software quality. It has to do with what are the measures we can put in place to ensure that the software we are designing comes out and the best. Okay, so that's what unit 1 session 3 helps us to understand. Okay, then we now move to the more general problem solving techniques, because software development life cycle is the formal framework. Now, when you have a problem, how do you convert problem, or how do you move from problem to programming solution? Okay, how do you move from from one to the other? Okay, so usually we would do what we call the problem development life cycle, and then we'll do program decomposition and modularization, and then we'll use one of the problem solving strategies to hit or to design or to develop the software system. Okay, are we okay? Please ask questions. Okay, if I'm going too fast, please draw my attention. Okay, so I can slow it down for you. Okay, that's a question. It's a question. Okay, so please, the defects same as bugs? Yes, please. Yes, please. Okay, so the defects are another name for bugs. Okay, Mr. Seth, you have a question?
Yes, please, the processing unit. I also heard
hardware.
about, yes, the TPU and NPU. Are they also processing units?
Yes, TPU. Yes, TPU is a special computers which do mathematics. Okay, TPU stands for tensor processing unit. Okay, so we have some computers which do mathematics. Okay, like for example, graphics processing units, GPU. They have a special chip on there which does tensor processing. Okay, I don't know if you've heard about a company called NVIDIA.
Yes,
NVIDIA.
yes, sir.
So NVIDIA builds special chips for adding additional functionality to your computer. For example, if you just buy a normal laptop, but you want to use your laptop for AI, then you go and buy a TPU from NVIDIA, you plug it into your machine, and then your machine can now do processing there and there. Okay, so because some of the processing, it takes so much memory. Okay, so what the TPU does is to take over those mathematical processing so that your computer will not maybe take too long when it's doing those processes. Okay.
Okay.
So they are special. They are also processors, but they are not CPU. Okay, they are not CPU.
Thank you, sir.
Yes, you're welcome, sir. Okay. So during problem solving, okay, we try to understand the problem and then try to move from the problem to the solution of the problem. For example, if any of you is hungry, your first point would be to try and understand what's actually wrong with you, which is the hunger. Okay, then you move from now trying to find a way to resolve the hunger. Okay, do I eat? Do I go and buy food outside? Do I cook? Do I eat? So you decide on an action. Then you carry out the action. You go and buy the food or you go and eat. Then afterwards, you now test to see whether you have actually solved the problem or not. You test to see whether you have solved the problem or not. Okay, so these are ways you solve or resolve a problem. Now, the general problem solving strategy that is written in your document or is in your book, okay, has about, I think, 4 steps in there. And so we'll discuss it. And you can compare it to maybe ways or informal ways that you use to resolve or solve problems. How do you resolve problems? First and foremost, you do something called a problem analysis. You try to understand the problem. Okay, so you try to see what the problem is talking about, what the variables of the problem are, what type of problem even it is in the first place. Then you try to write a plan, a way the problem can be resolved. Okay, you design a kind or a type of solution to the problem. Then you try to carry out that solution, the plan that you have written. Try to carry it out, and then you try to test whether the plan has been resolved or not, or whether there are some things that were not done properly. Okay. Now, can someone come up with an example of how you, any problem, not necessarily computing or IT, but how you have gone through the various steps or stages to resolving a problem? Can someone help us with that? Can someone help us with that?
Sir, please come again.
Someone help us with how you have used maybe these 4 steps, maybe informally or formally, to resolve a problem in the past. Hello? Yes, do you understand it now?
Yes.
I'm waiting to hear whether you can, yes, relate these 4 steps that we're talking about to real world problem solving. Okay.
Hello?
Yeah, hello. I'm waiting. Can you relate with one of the maybe how you have maybe used problem analysis, design, and then carrying out the problem and then debugging, something like that? Something really, so I gave the example of the food. Okay. So for example, when you are hungry, it's a problem. How did you solve the problem? You designed a solution, then you carried out the solution, and you tested whether the solution is correct or wrong. Now, how have you used something like that, similar in solving a problem?
To me, I've used it in troubleshooting my computer one time. Hello?
I'm here. I'm listening. I don't want to disturb your.
I used it in troubleshooting.
So you did how do you call it? You did analysis.
I'm on the way.
You did analysis.
Yes, please. So my PC was having a problem. So it was it always boots on the way then to stop. So that was a problem. So I was analyzing the problem according to my analysis. So I was predicting that it will either be from the RAM or it's going to be from the operating system. So I now designed a plan to solve the problem. And one is removing or changing the RAM. And the second plan was to clean it. If it doesn't work, then I'll change it. If it doesn't work, then I'll work on the operating system If it doesn't work, it means I have to send it to a specialist. So that was a plan that I designed in order to solve the booting problem. So I now carry out the hypothesis. That is the implementation of the plan. So I carried out the first plan was to clean the chips of the RAM and insect it back. So when I did carry out that plan, it works for me. So a friend.
Let us.
Ernest, mute your mic. Ernest.
Okay, that's interesting. Okay. Thank you very much. Okay, thank you. Okay, another one is in by Titus. Okay, so I'll read. Titus is a very long one, so I'll try and read it myself. Okay. Okay, so let's look at the next one. Now, there are some techniques we can use in solving problems. Okay, IT related problem solving. Okay, so we have something called divide and conquer. Divide and conquer simply meaning that we try and, instead of solving the problem as a whole or one piece, we split the problem into small pieces, solve those small pieces, and then combine the solution of the small pieces in order to solve the big problem. Okay, then we have another problem solving strategy called the dynamic program. Dynamic programming here means that we try and solve the problem, instead of solving it recursively, we solve it in such a way that when we know the solution to the small, to any of the parts of the problem, we don't expand all the parts of the problem space, but only expand the part of the problem space which we do not know the solution for, and then we combine quickly all the solutions. And then we have another problem solving strategy called greedy algorithms. So these are kinds of classes of problem solving strategy or techniques where we can, or we are always looking for the easiest or the first solution. Okay, so we call them greedy because they only look for the local solution and they don't look for the global solution to the entire problem. And then we have something called backtracking. Backtracking here simply means that when we are looking at a set of solutions, when we pass one or two of the solutions and we cannot find any more solutions, we can return back or go back to previous solution that we have found. And then heuristic, simply the kind of solution or problem solving strategy where we have maybe something like an oracle, or we have pre-knowledge of the problem and the solution. And then pattern recognition has to do with what? Identifying certain structures in the solution space and using that one to determine what the solution is. For example, if you have a problem of maybe fingerprint detection or facial detection, okay, so your machine can learn a face and then use that face to now help you log in every time you need to log in. Okay, that kind of solution, or that kind of, yes, that kind of solution space is what we call pattern recognition. Okay, so very, very important. So these are different ways problems can be solved, or different strategies that problems can be solved. And in fact, there are more. We're going to look at them critically during this next session. So in the next session, we look at algorithm design. Okay, so in algorithm design, we want to understand what an algorithm is and look at some of the defining or some of the key characteristics of a good algorithm. And then we're looking at the different kinds of algorithms that they are used. They are similar to the problem solving strategies. And then we'll look at some design techniques. Okay, so first and foremost, what is an algorithm? An algorithm is a sequence of steps that are followed, right? Non-ambiguous sequence of steps to solving a problem. So for example, we want an output. We want to get the names of all the students who are in maybe math, the math class, the BSc math class. But we have students from psychology, we have students from an IT class, we have students from computer science class and the math class. So how do we get only the students who do math, right? So we have to find a way where we will pick a student and then determine whether the student is in a math class. If the student is in the math class, you put the students in the math class. If it's not in the math class, put the students in another category. Okay. So this strategy of deciding or doing or sequence of steps we take to solve the problem is what we term as an algorithm. Are we okay? This strategy is what we term as an algorithm. So generally, an algorithm is a sequence of, or an unambiguous sequence of steps we use to solve a problem. Algorithms can be written in different ways. In fact, they can be written just as maybe like pseudocode. We can write them as words. We can write them as, we can draw them as flowcharts. We can even write them as programming code or programming language code. Now, what algorithms are is that algorithms are like recipes. Okay, so if you've seen a cookbook before, the book that we follow to cook food, okay, you notice that an algorithm looks similar to that one. The cookbook tells you how to cook. The algorithm tells you how to design the software solution to a problem. Okay, now what are some of the key characteristics? We say that algorithms have to be correct, or they have to have a correctness characteristic. When we say correct, what we simply mean is that they have to produce the expected outcome. If I want only students in mathematics, I shouldn't get a case where at one time I get students in mathematics, at another point in time, I get students in mathematics and IT, when I only want mathematics, okay? They have to be correct every single time with different kinds of inputs, okay? Algorithms also have to make efficient use of memory, have to respond in good time. If an algorithm can solve a problem in 2 days, and another algorithm can solve a problem in just 3 minutes, okay? The difference between the two, or the choice between choosing which one to use, depends on the time, right? So efficiency, space complexity, or time complexity is very important for algorithms. We call that efficiency of the algorithm. And then an algorithm should be able to be maintained. When we say maintain, we are talking about an algorithm where we can easily modify the algorithm. We can, when we know something new, we can add that new thing to the algorithm. Okay? You can add that new thing to the algorithm. And then algorithms should be scalable. When we say scalable, we are talking about when the algorithm's input changes. Okay, when the algorithm's input changes, can we still use that algorithm without having an effect on the efficiency or having an effect on maybe the time it takes to run? Okay, so that is also very, very important. Now, there are several types of algorithms. We have sorting algorithms, we have search algorithms, we have graph algorithms. When we say sorting algorithms, we're simply referring to algorithms that help us to do sorting. Okay, sorting here being what? We have a set of things or a list of things, and when we are arranging them in a particular order, right? There are algorithms like that, like linear sort. We have linear sort algorithms like what? Selection sort. We have merge sort. We have quick sort. We have different kinds of sorting algorithms. So we have search algorithms as well, like linear search and a binary search. They help us to do searching. So anybody who has done searching on the internet with Google, with ChatGPT, or with any of these tools has used a search algorithm. Then we have graph algorithms, right? Those of you who use things like maps, okay, you use Google Maps, okay? Google Maps is an example of a graph. What it does is that if you want to find your way from one point to another point, you want to go from Kaswa to maybe Malam, or Kaswa to Bawi, or any other place, okay? What the algorithm does is to look for a path from Kaswa going through all those points to Malam or to Bawi, okay? Then greedy algorithms, you're looking at examples of algorithms which find local minimums, okay? Which find local minimums, okay? So those are the different kinds or types of algorithm. Now, whenever we talk about algorithm efficiency, we normally would measure the efficiency of our algorithm in terms of something called big O, okay? Now, what big O is that big O is a way to classify whether the algorithm runs good or better, or the algorithm does not run good or better. Okay, so when we say maybe big O, it's a way we can use to compare. Okay, so we can say maybe if the big O is linear, it means what it means that when we increase the number of inputs, the size of the problem also increases linearly. Okay, or the size of the response also increases linearly. Then we can also maybe say that when we, for example, an algorithm like maybe bubble sort is quadratic sort. So when we increase the size of the input, the response is quadratic. It means it's the square of the size of the input. Okay, so those ones are a way we can use to measure the algorithm efficiency. Okay, there are several algorithm design strategies. I already mentioned these ones before, and they are also in your slide or in your book at that level. Okay. Okay. So, any questions? Any questions
Yes, sir.
about
Yes.
that section? Okay. Yes. Any question? Okay. Any questions about that section? Okay. No questions. Okay. So we will quickly move to
Please, sir,
the programming paradigm. Yes. Yes.
Sir, there's a question. Sir, you were talking about the efficiency of the programming algorithm, and you made mention of the big O note, big O. Yes, and I wanted to ask, are we going to do some proof? Are we going to prove it? Because like
no,
mathematical
this course does not look at that. This course looks at how to program. Yes, I understand what you mean, but I'm saying that this course looks at how to program. It doesn't look at
okay,
into
all right,
calculating algorithm efficiency. Okay.
Yeah.
Okay, so we'll not do calculations. We'll just do that. Okay. Yeah, there's a hand up. There's a hand up. Mel Mark.
Yes, sir. You keep, sir. You keep mentioning our material, but like the material that we have, some of these things are not in. I don't know what there's a different material.
Pardon? You said you keep mentioning what?
The materials, like maybe I'm not pronouncing the right word. Handout. Okay, thank you, bro.
Thank you, sir.
You keep mentioning handouts that we have, but with what you are sharing right now, the handout that I've seen being posted on the page, this areas they are not in. So I don't know whether there's a different handout.
Hello. Should I open it for you?
As I said, the one that we have posted on
I can show you right now. I can show you right now.
I'm not challenging you. I'm trying to say like the one that has been posted on our page. This ones are not in.
Oh, you are. Can you see the manual, the model?
No, we don't. I think we don't have this one.
Oh,
I don't know if
So yes, we don't have
this
it.
one
We don't have it.
We are currently.
Say we don't have this one.
Oh, so which one do you have?
The one that we have is about a few pages. If I'm not like 36 pages.
Oh,
yes, exactly.
You don't have University of Cape Coast College of this.
No,
sir.
Yeah, we don't have this one. So what
which one do you have?
The one that we have is 36 pages, as I said.
Oh,
it begins with programming techniques.
Share it in the share it in the chat. Let me see, because this is what I was given.
Yeah.
Okay.
We are loving everything you are sharing, though. Like we are loving your lectures and everything. But this one we don't have it.
I'm saying share what you have and let me have a look. Okay. I'm not on your page, so I don't know which one you have.
But with respect, what you are talking about, was it shared by the code or was it shared by someone else? If it's someone else, then that's not the rightful source. But if it's from code, from Switch, then I presume it's okay.
Bro, what I'm going
Are we still talking about the material you have been given, or we are talking about something else?
I was talking about the material.
Please let's proceed. After he has done with the lecture, then we tell him to give us what he has, so that we will move on. Because this banter will not bring anything. Please.
Okay. I'll have them because I don't know what material you're talking
mute
about.
your this thing, sir. Mute it.
I don't know which material you're talking about, so I'll have them share this one with you. Okay. I also got this one just today. Okay.
Okay, we'll be grateful for that. Thank you, sir.
Okay, so let's go back to the book.
Mute your mic.
Inusa.
Who is Inusa? Can I mute the person? Okay. So the guy is off. Okay. Thank you very much, sir. Okay, so last session looks at programming paradigms. Programming paradigms, basically we're looking at the distinct styles or the ways in which we can approach the development of programs. Okay, so here now that we've seen the various kinds of programming languages, software, types of software and all those things, now we will ask ourselves, so how will we write the software? So how we write the software is what we call the programming paradigms. Now there are various ways the software can be written. Okay, now the paradigm or even the type of problem influences the programming paradigm. Okay, so for example, if we have a problem that we need to solve it on the web or the internet, we might decide to design a website, or we might decide to design something called a web app, right? So those things influence the kind of programming language, the kind of programming structures, the kind of things we can use in our software development. Okay, so that's what we mean by the programming paradigm. Okay, understanding the different types of programming and styles that can be used. Now, and the reason why they are significant is that programming paradigms are largely dependent on the type of problem that we face. Okay, so if we face maybe develop a web, like I said, a web-based problem, or maybe we wanted to build a mobile app, we cannot use the same techniques we use to build mobile apps, to build web apps, or to build desktop applications. Okay, or if you wanted to build maybe a small software, it will be entirely different from how we will build maybe a large or a big software. Okay, so the programming paradigms influences the style or the design or the approach that we use to design the software system. Now, there are several of them. The basic ones or the more common ones, example include what? The procedural programming. So procedural programming largely focuses on what? Writing and structured programs which execute step by step. So for example, you want to solve a problem and you are solving the problem by writing instructions which run one after the other. We call that type of problem solving procedural or structured programming. Right? If the problem is small or the solution is quite manageable, that's what we call procedural programming, or that's what we tend to implement with procedural programming. Then when we have large types of programs, okay, and we can only solve them by dividing the problem into, or dividing the solution space into what we call objects, then we go in for something called object-oriented programming. Here, we can use things like encapsulation, we can use features like abstraction, you can use features like polymorphism, inheritance. All those are classes of or characteristics of object-oriented programming, which help us to build modular and well-defined pieces of code. Okay, so if you are building a very large application, you use object-oriented programming. Okay, then functional programming is a type of programming style where we try to build functions, or we try to build groups of code which do specific things. Groups of code which do specific things. So there are some features like what we call immutability of functions, pure functions, immutability of functions, variables. Those things come as a result of functional programming. Okay, so if you want to do some mathematical programming like MATLAB, or you are doing some concurrent programming or parallel programming, you use functional programming. Then we have another type of programming paradigm or style we call reactive programming. So reactive programming, when you want to build programs which run multiple things at the same time, we call that concurrent or asynchronous programming. Okay, we use reactive programming. Okay, so you are building maybe UI environments where maybe you click on something happens, or you push a button and something happens, that kind of thing. We call that type of programming reactive programming. Okay, then we have declarative programming. So if any of you have ever seen a database, okay, database before, right? The way databases are written is an example of declarative programming. We just write the instructions, select maybe all from so-and-so database, and then all the records in that database come. We describe what we want with the syntax, right? The syntax in declarative programming describes what we want. And when we describe it, then when the engine runs it, or when the compiler or interpreter runs it, we get the results. Another example is HTML. Your web pages are built using a language called HTML, CSS, and JavaScript. Okay, so those are examples of declarative programming. Then we have logical programming. All those who do AI and machine learning, okay, programming languages like Elan or Prolog are examples of logical programming. We write logical statements, if, else, if, and then true, false clauses. And sometimes we call them conjunctive normal form clauses. Okay, we write statements like that. Once we write statements like that, the machine will evaluate the statement and return a response. Okay, so those are the various types. Now, how do we select a particular paradigm, a particular style? How would we pick a particular style? We pick a particular style based on the domain, the space where the problem is coming from. So, for example, if the problem is from maybe if it's a very big problem and the solution is going to be also big, we use object-oriented, okay? Because object-oriented is useful for things like that. You want to build maybe a graphical user application, okay? An enterprise. Enterprise means a business application. You want to build a very sophisticated simulation software, we use object-oriented. If the solution is maybe in the space of mathematics, data processing, or data mining, those kinds of things, we use functional programming. If it is AI and the rest and the like, where there's logic, we use logical or declarative programming. Okay, then sometimes it also depends on the scale and the complexity. For more complex applications, we use OOP. Okay, OOP is well suited for more complex. We have something called MVC, Model View Controller. That one is also suited for very large scale applications which use lots of interfaces, okay, and lots of data. Then we have, if it is simple application and it's just something like teaching students and the rest, we use procedural or imperative approaches, okay? Then sometimes your team members, based on their skills, you decide to use a particular programming paradigm. So if you employ me and I can only write in OOP, but you want someone to write in maybe declarative, I can't do declarative. So you go and grab someone who can do declarative, or you employ someone who can do declarative. And then sometimes too, it largely depends on the kind of support. Okay, when we say support, we mean the kind of partnerships you can have in that language. Okay, So maybe that language has a lot of people who read or write in that language, and so they can support you when you find yourself in difficult situations. So all of those or all of these are multiple, or all of these are lots of ways in which we can choose a particular paradigm. Like I said, paradigms are only the styles we use in the programming. Okay, so at this point, I would want to ask if there are any questions, and then we answer them, and then we end our lecture here. Okay, then we will continue with Unit 2 the next time we meet. Okay, I will ask there's somebody moderating or somebody monitoring our meeting, so I will ask them to help you with the resources, and then you can maybe get access to the resources, and then we can move on from there. Okay. But if there's any question, please throw it at me. Let me answer you, and then we can call off our meeting. Okay. Hello. Questions? Isn't there any question?
Sir, please, a question.
Yes, sir. I'm all ears.
Sir, please, the various programming paradigms.
Yes.
Would there be an instance where some of the programming paradigms will be integrated, like some form of integration?
Certainly. Okay, so OOP is actually a very sophisticated. It's been around for a long time. Okay, but if you look at OOP proper, you see that there is structured programming. Okay, in OOP there's functional programming. In OOP, there is some form of declarative programming tool in there. So you see that there are various styles. They can be integrated together to make the development of the software easy.
Okay.
Yes. So if you know a couple of them, you can add it together and help you make your development easy. Okay.
Yes, sir.
Yes. On the web, we have something called document object model. Okay. So the document object model is also a kind of programming paradigm we use on the web. But you can also see that on the web too, we do declarative. Okay, so it's just a mixture, right? What works and helps you to build your software, you can just put it together and then build your software. Okay.
Yes, sir.
Okay.
Thank you, sir.
You're welcome, sir.
Okay.
Hello. Hello.
Hello.
Yes.
Yes,
Any
hello.
questions? Any questions? If there are no questions, then.
Hello, sir. Like,
yes, sir.
The silence is, to me, the meaning is clear there. Like, we've enjoyed your
so
lesson.
all of you understand everything. Okay, that's
we've enjoyed. I wouldn't say we understand. We've enjoyed your lesson.
Okay,
And,
thank you very much. Thank you.
Thumbs up. Like, we want to see more of you, and then maybe in subsequent ones we might ask more questions. But you've delivered. We've enjoyed it.
So I'll let
appreciate.
Okay.
So we only will ask about the materials that you have.
Yes. I'll give it to them so that they can give it to you. Okay.
Yeah. So that don't get worried. We are not asking questions. It's because of the fact that you delivered.
Okay. Thank you.
Appreciate it.
Okay.
Thank you, sir.
Okay. Thank you very much. Okay. So I'll get in touch with them, and then they will help you get access to all the materials. Okay.
Yeah, including your slide.
Yes, I'll send. I have to send it to my coordinator before. I have to share with my coordinator before I get to.
No,
okay?
no, right.
This is my personal slide, so I have to share with her first. Okay.
Yeah. Tell your coordinator we want your slide as well, in addition to what.
Okay. Noted.
Thank you.
Well done.
Okay. Thank you very much. So I'll see you guys, God willing. Okay.
Thank you, sir.
Thank you, sir.
Okay.
Christian. Hello.
Christian.
Hello, please.
Christian.
Yes, I'm here.
How far?
I'm
Just
here.
join the link. Oh, what's going on?
Then you are late. You are late.
I'm late. How? What's going on?
We are close.
We are done. We are done.
Oh, you are done for the day.
Yeah.
The lesson, the
Yeah.
lesson is over.
Do you think you are going to close at 8?
Come again.
I'm aware the lecture is supposed to close at
The
8:30.
lecture is gone and the
No,
lesson
no,
is
no,
over.
no.
Leave my mocha.
You are late.
Oh, Charlie. So how was the programming lecture? How was it?
Superb, bro. Superb.
Is Clifford not here?
Come for tutorials.
He's out of coverage.
Christian Sogono.
Yes, I'm here. I can hear you.
Please take me through the lecture. 5 minutes. or this is not your field.
Come to my DM and say hi. I will send everything to you. I recorded it, so you just send me hi. I will send it to you.
Please, which page are you? Are you on all study centers?
Yeah.
And your name is Amu there. By your number?
0245 111106.
Okay, let me type you
0245 111106.
111106.
Yeah.
I'm okay. I'll hire you straight away.
Okay.
Mr. Christian.
Yes, Lord.
Charlie Alpha, you are me, so.
Charlie is true. My network give me problem.
The way I miss you is color psychology, you know.
I think we'll meet again in color psychology this semester.
Really? Me, I don't want to do any course. I've written already.
We'll meet again, don't worry.
How I wish the mathematics for computing too will be scrapped, no?
We'll do it next semester.
Really? And I know that will be your last mathematics.
Yes, that will be the last mathematics.
Oh, okay. All right.
So far, it's a course we are classing operating system.
Okay, Charlie. See you guys,
Okay, bro.
All right.